I have.
It was more to one of the references.
Yeah.
All right. So Theo, can you, oops, apparently I have to say yes. Theo, there's some people here who were not here last week. So you can introduce yourself in a second. But could you guys just quickly, so Theo knows who's here, just go ahead and say your names. And so for Francois, that was very super important because he was part of this discussion last year where we had this crazy idea that you're now working on.
Thank you, Alicia. I'm François Boulanger. I work in Paris. I'm interested in ISM physics and local bubble.
Hi, I am a grad student in Columbia, currently working with Mary Putman on like ISM and CGM physics.
And Avery Kim.
Avery Kim. Yeah, sorry, I'm Avery Kim.
I'm Laura Fissel. I was here last week, so
You know everybody. But Laura is a huge expert on polarimetry. Very important.
I'm Laura Foch. I'm working with Joao as a PhD student on the ISM.
And so Laura is here, but Joao is not here because I don't know whether you got the news, but Joao got COVID. Yeah, it's been very interesting. And Cameron also is from Joao's group. Okay, Cameron.
Yeah, I'm Cameron. I'm a first-year PhD student with Joao, and I'm working on galactic structure, specifically with the Radcliffe Light.
Are you guys just hanging out in the back, or do you want to introduce yourselves? Hanging out. I think they're just hanging out. Anyway, go ahead. Go ahead.
I'm fine, you know me.
I'm Gina. I was here last week.
Right.
I know some stars.
Gina's also a big polarization expert.
Hi, I'm Olga. I'm a chemistry student to Harvard.
Olga's going to be a first-year graduate student in a few weeks.
Jaime Pineda, high density interloper to this group. So
Yeah,
very
and he's like a
interesting.
20-year
Kinematics.
graduate student at Harvard too. Oh, and here's Susan.
Hello, I'm here.
And this is Susan Clark.
Hi.
And Susan is also very interested in this project and potentially wants, what we've decided, by the way, everybody, that because this started at the Interstellar Institute, the paper that Theo will write as a result of their summer project will be called something like the Interstellar Institute model of the, or map of the magnetic field of the local bubble. So whoever wants to sign on and do something should sign on and do something. So Francois, you already did something. You helped out the idea. Anyway, so Theo, can you take it away and just give us an update and just put in a little bit of the beginning for the people who weren't here last week, please?
Perfect. Yeah, I guess how much have you told them?
Well, about half the people here saw stuff last week and the other half just hear that there's some kind of three-dimensional map of the local bubble in magnetic fields and they're curious what it is.
Perfect. Yeah.
And also, I didn't
can,
introduce you, so feel free to introduce yourself.
yeah, I'm Theo. I'm an undergrad at the University of Virginia. I'm working with Alyssa this summer, and my pronouns are they and them. But I can pull up maybe the Google Doc with some of the plots quickly.
Sure. And Theo's also been talking to Juan a lot and a little bit Jesse Hahn, for those of you who know Jesse, and Catherine a teeny bit, but Catherine's outside talking to another student. Sorry, Theo.
Perfect. Is that zoomed in enough?
Yeah, we can see that. That's sure.
Cool. So I don't know what Alyssa shared, but this summer we've been combining some Planck and starlight polarization data to make a full 3D model of the local bubble's magnetic field over its surface. And so that started, I guess, with a pretty naive geometric constraint. I'll get a good video of that up. So taking the,
they'll explain.
Yeah, taking the very naive assumption that the majority of the polarization we see in the plane of sky at high latitudes is coming from the bubble as the last surface between us and the rest of the universe. And so assuming that the polarization vectors that we see on sky are just projections of 3D vectors that are tangent to the full surface of the bubble, so that we see a constrained, shorter version of field from our orientation, and so that by combining that constraint with the orientation of the bubble, we can then kind of deproject and back out a full 3D set of vectors. And so that ends up looking something like, let's see if I can pull this up at the same time. Something like this. So the gray surface here is the 3D model created by Pelgrim et al. In 2020 of the local bubble surface, and the red is showing a full 3D vector field over its surface of the magnetic field. And so we can scroll around a bit over its surface. And so that's what we've been working on so far. We've also been comparing the 3D and 2D projections of this work. So this plot here is showing in the color underlying the plots is the distance to the surface of that Pelgrim's model, with low colors, with high colors being closer. And then overlaid is this drapery plot showing the plane of sky magnetic field. And so we see associations, we think, between distance and local kind of distortions in the field. And a bunch as well, but I'm not sure what people are interested in.
So Theo, what is the resolution of your map? What is the angular resolution of your map?
Yeah, I think we have a maximum resolution of like about 20 parsecs.
No, but in terms of angular.
This is the
Yeah.
the GLEAK map, the one with variable with changing over the sky.
Because if you go too high resolution, your plane of the sky is turbulence dominated.
Yes, right. We had a long
Yeah.
discussion at the very beginning of the project about, too big of a plane and it's not tangent to anything meaningful anymore, and too small of a plane, you wind up with those kind of problems. And so, do you remember in an angular size what the sort of smoothing is, what the 1 pixel is?
I smoothed it to 2 degrees on sky overall.
That's fine. Okay, that's fine.
I would have used a much bigger beam, but because I play with things like this, but I use a multiple model, and I don't go to very high multiples.
Right. I don't know. All I can say is it seems to have worked. So we'll keep looking, and then maybe we can do better. But that's why we're having the conversation.
Well, so with a 2-degree smoothing, you will get rid of the problem of the galactic plane, but the generic map, or however it's pronounced, I think at high galactic latitude is like 5 degrees. Sorry.
Yeah, I think for me, I will smooth much more. Yeah.
Well, what's interesting is that, and Theo has a comparison with, I was worried when I saw that beautiful thing with the red vectors that some of that was just the projection of, like maybe it's just a totally straight field, and that's what it looks like when you wrap a straight field around a curvy surface. So Theo, actually, oh, here it is. Thanks, Theo. So the blue is the just geometry. Yeah. No interesting anything in the field. So that's just a totally straight field wrapped around the same surface. And you can see that you do get structure in the
Wait,
red.
so
that isn't
left
there.
is the Pelgrim's model. And
They're both Pelgrims. The only Pelgrims part of this is the shape of the surface. And then the left is taking the Planck polarization and just saying, if you see a vector in 2D and it's inclined, the way that the bubble surface is inclined according to Pelgrims, what is the true 3D vector if you add that third dimension in? And then on the right is if you just had a totally horizontal according to the galactic plane, just totally straight uniform field, and all you're doing is wrapping it onto that surface, then you get what's shown in blue, and you can see that they're different. So there is actually some information that's not just about the projection of what would be a straight field. So, and then, but I was really impressed. Can you go back to the 2D view there? So when you see that map, if you look, you have to look carefully. Not that carefully, actually, but so, the color is the distance, right? And so the question is like, does your eye, just to start with, see correspondence between the color and the swirly patterns, essentially? And I would say yes. I mean, sort of look at stuff like this is extremely impressive to me. And then whether you should believe the polls is a whole other question, like going back to our discussion of an hour ago, how much do you believe the model at the top and the bottom? Laura might tell you not to, or Gina said not to, right? You said you don't like the top and the bottom of this local bubble?
No, I was talking about the polar rift and how the.
Oh, just the, okay, so just
stars
one
are
place.
tracing a polarization that's further out and not the local bubble.
Got it. Well, well, we'll have some of that. So there's new stuff. Okay, anyway, whatever. I think this is not random.
So, okay, well, my group has been doing something kind of similar, so maybe we should just join forces. But
Yeah.
our goal was to, so we've similarly been using the tangent plane, but our goal is to actually test whether these assumptions make sense instead of just like assuming them.
Yeah.
So in principle, a thing that you can look for is variation between variation in something like the polarization factor or the S factor of the plane of sky and polarization dispersion with the inferred inclination angle that you get, assuming that the field is truly in the wall of the local bubble.
I think some of that is coming next. So sorry.
All right,
Keep
good.
going, Theo. However,
Not
nothing
to
whether the magnetic.
curvature or
That's not, we didn't-
Okay.
Yeah, sure. Go ahead. Just go in whatever order you like.
sure.
Especially
so-
the comparison with the distance, the constrained polarization.
Sure. Yeah, I can jump right to that. So we have a comparison here of some starlight polarization data with distances from Gaia, DR2, from inside versus outside of the bubble on the plane of sky. And it seems like, anyway, that stars inside of the bubble have a more random orientation with respect to this gray field, which is a 2D projection of the field that we've wrapped onto the 3D surface of the bubble. And so the red vectors are stars, the blue down here are stars, and outside seem preferentially more aligned with that surface.
What is the vector of stars say?
Sorry?
What is it?
The vector is the blue vector is the polarization of a background star, and they're separated into stars that are, the left-hand plot shows you the distribution of the distances to those stars. So the blue ones you see are outside the bubble, potentially far outside the bubble, but not too far, because you don't want to go get a whole bunch of the galaxy. And then the red ones are inside the bubble, and so shouldn't know anything if the field is really in the surface of the bubble.
So what is LB surface? Sorry, I'm missing this.
Local
Oh,
bubble.
sorry, local bubble surface.
Yeah, but what does that mean? Is that the Planck map draped on, or is this just following the contours of the local bubble?
It is both, I guess. So it is the Planck map directly. The way that we've set up our projection is that so in 2D, our 3D vectors will appear identical to the 2D projection of Planck
Essentially,
vectors.
Planck versus starlight polarization?
Right. So in other words, just you have to remember that. So we were sitting around, Francois and Katya Ferrier and I and Joao last summer. And I was like, what if we just did this really dumb thing and assume, this is Susan's point, it could be totally wrong, okay? But just like assume that the field is almost completely confined to the surface of the bubble. In which case, if you say that, then and then you also say that the polarization is produced all in the surface of the bubble, which has to be wrong, okay? But if it's primarily produced in the surface or in that, thickness of the bubble, then it's not going to look too wrong, right? And what Theo is saying is that because those are the purely dumb geometric constraints, that means that projecting the 3D map that they made back to 2D should look identical to the 2D map, because that's what you started with. And so that projection and deprojection is really all that's been done. And then what you see is comparisons with stuff that's only 2D, which is the background starlight polarization. Right? You get it? So there's nothing fancy. That's the hard part to appreciate, is that I mean, while it's interesting and fun and kind of seems like it works, it's the simplest assumption you could possibly make.
This is a very naive question, but is it possible to kind of figure out the width, the thickness of the bubble layer by just comparing the correlations, like this correlations within the stars inside of the local
I
bubble?
don't think that's a naive question. I think that's an interesting question. It's not something, I don't think, Theo, you haven't done anything like that, right? Yeah.
No, not yet.
Student has.
Vincent Pilgrims has, and Gina?
Vincent is in the extinction.
Yeah, okay.
And so he has an inner and outer surface from the extinction. The stellar polarization sampling and distance space is not good enough.
We haven't tried.
A little bit. You can do it. In principle, you definitely can do it. In principle, you can do the whole thing. If you have enough stars.
So how are you thinking of testing whether the assumption you've made is correct?
So the goal of this paper, Theo, can you just show the rest of what you have? So we can move on to other people showing stuff too. But the goal of this paper is just to say, if you make these assumptions, this is what it looks like. And there'll be some statistical, a little bit of statistical comparison. And so like, we might want to do something to compare the background starlight polarization and the Planck polarization a little bit more systematically than here's a picture. And Theo started some of that, and you'll see some measurements by distance here in a minute. But all of these other questions, I'm hoping are for like future other related.
Wait, so what I just said we're working on, you said that's coming. You actually have not done that yet.
No, it's
We're planning
coming. You'll see.
Okay.
do that, Susan. So we were planning to do the comparison between the polarization orientations and polarization fractions as a layer on top of that to see where are we fine, but we decided to trace the line before it. So this would be like the template of what would be a model of projecting everything into the local bubble. That's where we trace the line. Theo is going to be showing some maps in a second or of the surfaces where the local bubble is perpendicular to the plane of the sky. So those would be places where we would expect a lowering of the polarization fraction, or for example, in the S2 map, we would expect that there's like a boundary, one of those spaghetti that we found in Planck. We are not going to do that yet. So this is a product that you can actually use to fit into your analysis, because it's giving you information about the local bubble only. So,
Go ahead, Theo.
Is this what you were thinking, Alyssa, of showing?
Yeah, the plots that you
Or-
sent yesterday, all of them. There's just 5 of them, right?
Yeah. Sure. So this is the points here again are from the starlight polarization data, showing polarization fraction as a function of distance just from the sun. And then the coloring is whether that star just happens to fall within or outside of the Pelgrim's map of the local bubble. So red is inside, blue is outside. And stars outside of the bubble have a significantly higher polarization fraction. And then these are very new plots, but so just taking random small groupings of stars along a given line of sight, and then doing an average polarization fraction along that given line of sight as a function of distance. So each solid line here is showing the average polarization fraction along that given line inside the bubble, and then it transitions to dashed when it reaches outside with the surface marked by a square. And so with the big caveat, these plots are very fresh. We do see a kind of common pattern of rapid increase and then plateauing in overall polarization fraction after you've reached the surface of the bubble.
So just to make a comment, so usually in extinction polarization, you expect as you go through a larger column, the polarization to increase. So another interesting test might be to normalize by the extinction, right? And calculate the polarization efficiency, because that should be, that should average out the integration over column density.
That is a good point, and you had said something about that, and so I don't remember whether that was already done for these data.
we haven't done it. Yeah, that's what we reported in Planck 19, which is P over AV.
Yeah, so that's what I would sort of expect to give information about the inclination angle rather than just the polarization.
Yeah, my only problem with that is, as we were discussing at lunch, I have no faith in the fidelity of polarization percentage as measuring much about anything. Because I believe that it's this horrible, mixture of geometry, grain alignment, strength of magnetic field, column density, and I just don't know if we could.
There's no variable grain alignment on large angular scales.
Hopefully
in the high
not.
galactic latitudes,
Hopefully not. We'll leave that one out. So we'll just do
And so
geometry, column
if you're worried about that, Alyssa, dust extinction should be a cleaner measurement than Planck, right? Because you don't have all the temperature effects as well.
Well, also you don't have as big a line of sight.
Exactly.
Yes, it should be, right. And again, so all of these are like super good questions, and we should let everybody else show other stuff. And this is only like meant, this is an undergraduate project, which is pretty good if I.
No, this
you know.
is amazing.
It's
Thank
like-
you for.
Yeah,
Thanks
it's just,
so much.
here's what happens if you make this set of assumptions and
Yeah.
ta-da, now everybody go do the, is the curl of the bee the right, constraint to not violate Maxwell's equations, et cetera. So Susan, you wanna, Theo, was there, can you just show quickly those curvature plots? Because I think one
Yeah,
was,
sure.
and then one, you wanna, and Susan, you wanna show anything?
No, it's okay. I just want to check.
Okay, sure.
Also, my laptop is.
So this one, we're comparing this, or I was comparing this to S2, to see if these are the places where the surface of the local bubble would be perpendicular to us. We would expect.
Wait, so just to explain, the blue is where it's poofed out, if you look at the 3D thing on the side, and the red is where it's curved in, and then the white is where it's relatively flat, so. And then the colors are the same, right?
So this is like the Hessian of the surface.
Kind of, yeah.
This is the second derivative.
It's not the second derivative. You can just calculate the normal to the line of sight vector. Yeah. So if you want to call it that.
It's labeled curvature. So
What is the calculation here, Theo, that gives you the colors?
It's calculating, I think, root fitting to local areas. The mean curvature PyVista does it natively through BTK. Yeah.
It's related to, it effectively is the same, but it's calculated from the line of sight and then the angle, kind of the normal to the local bubble and the line of sight. So if it's like this, it's white. If it's like this, would be blue, and the red one, yeah.
So it's more or less always white or mostly white.
White will
Here
be,
would be completely white.
it will be completely white. Thanks, Lisa.
Okay.
So this is the kind of things that we want to compare with polarization fraction and stuff like that. But before we get to that, I would like to see what comes out of FM simulation, because in FM simulation we actually have the 3D magnetic field. So we'll be able to validate if we should expect this kind of things from a local.
Which simulation is that?
Okay, so I guess now it's my
You
turn.
just joined, do you have the Zoom link from Slack?
Yeah.
I'll just let you.
I'm sorry, but I will have to leave shortly. But maybe, yeah, we'll have
This is
a,
really awesome work, Theo.
yeah,
Yeah.
it's beautiful. Thank you very much, Theo.
Thank you.
If you want, we can label this paper one and then everybody
Yeah.
join and then write whatever other paper should be written.
If you guys have to go, I can show this tomorrow.
Because I haven't come at 4.
I think Theo also wants to see what, I mean,
Okay.
we've already seen it, but maybe show it twice.
So of course this is work in progress, and it's all FM's work.
Hi, Joao, how are you feeling?
Right.
No, seriously, really? Are you?
Yeah, I don't feel anything.
It's COVID, it's fine. There was some new stuff that Theo showed as a function of distance. Juan's going to show stuff now, though. Did you see that in Slack? Joao?
No, I was in another meeting.
Oh, yeah, no problem. But Theo, can you just send that to Joao too, please? Thanks, because he'll be happy.
Thank you, Theo.
Yeah. If there's anyone else with these, fine with that. Like,
So which link are we sending? Can you
also
send me the link
It's in,
again?
yeah, sure. It's in Slack.
do what you need to
It's
do.
in the local bubble. The thing
Are you-
that we're on with Theo, it's already in there. Yeah, I'll send it again now.
Oh, thanks. Yeah.
I'm sitting here reading that.
Yeah, mine too. We need new computers.
Wait, oh, I'm not sharing my screen. Okay, well, I'll send it to you directly. Hang on one second.
I'm sorry, I have to run.
It's in the footer of every email I sent. Get it.
When you
I'll show you.
Oh, thank you. I'll also put it in the Salon meetings group. It was, so now you have it in the local bubble. You want me to send it to you directly? I can do that too.
I'm connecting.
You got it? Oh, okay. I just have to let you know. I lost it. Yeah. Are you waiting for me to admit it?
Yes.
There you are. Okay, got it. That's my.
No, it's like purple.
So,
That one. Okay.
yeah. Theo, can you hear me? Yes, okay. So Theo, I don't have a plot to show where initially began, but this is a simulation of a 500 parsec box of ISM that is stratified. So artificially, we put a gravitational potential, and what you're seeing is that simulated galactic plane from the top. So from left to right, what you're seeing is just evolution of this ISM. And what you see in blue are local bubbles that we pick by some arbitrary measure. If you take all of the bubbles that you get from this simulation over time, and you look for the ones that have the right temperature and have the right density, we reduce the population from like thousands of bubbles to just a few. And the one that we pick, so we just pick one that has an open cap and a closed cap. So what you're seeing there from left to right is, so the one in the rightmost panel is seen from the top. So you see it has very well-defined walls in that galactic plane, but it has an open cavity towards the bottom. So we picked this one because we wanted to see how is the polarization when you have an open bubble. This is a plot that we obtained from the ray tracing. So here in red and blue, you're seeing the changes in polarization. So blue means decrease in polarization. This is mostly because of geometry of the magnetic field. Red is increasing polarization. And again, this is ray tracing. So it's as if you could do like slices of Planck for different radius from the observer.
That'd be nice.
Oh, that would be amazing. So we applied the same method as Pelgrim's to define the inside of the bubble and the outside of the bubble. So just some threshold in density. Of course, the bottom of the cavity doesn't have a well-defined cap. So this is the bubble, and this is the bubble thickness that we would get. And this is how that bubble would be projected on the plane of the sky. So this is the same plot that you're showing in yellow and black. So this is the same one. This is the inner surface of the bubble. So as you can see, we communicate in multiple languages, which makes everything fun. Yeah, so now we go towards these plots that you're familiar with. So these are just some selected lines of sight. So this is the increase in column density. This is the change in polarization, and this is the change in polarization fraction. So actually with polarization fraction, you depend on the geometry of the field. So you don't expect that this monotonically increase. But for example, for the brown line of sight, you have a peak of polarization and then you depolarize behind because you have a galactic plane and that has whatever field it
And
has.
this is what Laura was asking for.
That is what Laura was asking for.
So Theo, that we can make that plot pretty easily, right?
That's what?
That's emission, not absorption. It's not the same.
Oops, sorry.
Right?
Yeah, that is emission. That is
That's not what Laura was saying.
What does she want? Oh, she wants the same thing, but for background starlight.
Yeah, so she wants, divided by AB. So she wants P over A.
Yeah, I just wanted to figure out what that was.
Yeah.
Sure. I'm sorry, Gina. There's some fan here and I can barely hear you.
I will speak louder.
Sorry.
So this is the same, but now as 2D histogram. So this is changes in column density, in polarization, and polarization fraction. So the different lines correspond to the median. So this is just the way in which we see the bubble. So we see a peak in column density, but also in polarization. This is the magnetic field organized in the walls of the bubble that cause that peak in polarization. So how does our local bubble look? Like this. So you see, there's a few things that are interesting. So the first one is that there's convergence of the field towards these poles, which actually are the places in which also the mean field orientation in the box converge. So you don't lose memory of the mean field orientation in the box, or if you want to call it the large scale orientation of the field, just because you have a bubble. You cannot mimic that. The other thing that is interesting is, so this is just the bubble. So there you still see, so this is everything. And this is just the bubble that we define as I showed you guys before. So maybe we have to increase the transparency or decrease the transparency, but also the poles converge there. So the convergence of the field in those two places are not dependent on the presence of the bubble. So the bubble has it, but also what is behind its orientation. What is interesting comes here, and I think that's the most interesting result. If you look towards the caps, you don't see the same thing that we see with Planck. You see this weird pattern, which is not at all the regular pattern that we saw. And this is because there's turbulence in the walls of the bubble. So it's actually almost impossible to find a bubble for which you reproduce the Planck homogeneous result towards high galactic latitude just with the bubble. You don't see the bubble towards high galactic latitude. Of course, you expect that in the open side of the bubble, but not in the closed side of the bubble. So if
What does the 3D field look like on the top side of that bubble?
That's what I was going to show you.
Good question.
Good question.
It was plugged.
So you see the field goes up.
Ah.
So in this projection, you can see that the field is closed, it's following the idealized model, but there's still turbulence. So the field goes a little bit up. So what you're seeing is the field just going up a little bit. And that is just because of the porosity of the bubble, it's because it's not regular. So that means the bubble would have to be very ideal and completely closed for you to reproduce the Planck pattern. So we think that what we're seeing in Planck is not just the bubble, but the large scale field. So Ephraim did some tests. I'm about to finish. I will take off. So Ephraim did a test just with the field that you would get just with an homogeneous magnetic field. So this is homogeneous magnetic field over the box. So you recover some of the large scale pattern converging towards the poles, just as we see with Planck, and just the bubble. This is just the bubble. So the bubble doesn't preserve that mean field orientation towards the
Can I ask a question then? So in the blue vector plots and the red vector plots that Theo has, do you see that difference when you tilt them to the top, Theo? Does the blue one look straight across and the red one has some kind of different structure, or does it also look straight across? I don't know.
Have a look at that.
The red one has some pretty interesting structure.
Okay.
You want to show it?
I'm not sure I have a video showing it. I can take a look if you want to.
You just open up the live thing if you want.
I don't have Python running right now.
Oh, sorry.
If you're willing to wait 5 minutes, I can get it up.
Oh,
but...
other people have plenty to say. We can all wait 5 minutes.
Yeah. Don't worry.
Laura.
Maybe so what are the poles converging to? Is this?
So if you have a field that's in the plane of the galaxy and then you just make that projection, it'll look like that.
Okay.
It's just a fact of the coordinate system, essentially.
Right, because it's going along the rotation, and then with the projection, it looks like.
Oh, you don't. It's not even. that complicated.
Even if it's
It's just straight.
It's just because of the perspective. Like,
Yes.
So if you take these lines and you project them into infinite,
Yeah.
they're going to converge towards two poles.
Okay.
That's kind of what we see in the Planck data, or we like to think, but we also see this very regular field on the top.
I do understand that, but like, is it the poles are there along the rotation or towards the center and outwards? Or?
Well, in the simulation, they're whatever direction, right?
Yeah, and
uniform field.
so I'm going to show you a simple
The
operation.
field is like the orientation of the train tracks, and the convergence is like looking out to the distance of the train tracks.
In the Planck maps, have you located points?
Yeah, that was the work of Andrea. So we could only use the southern. So is this? This is the plot that I did to explain to Ephraim. So you live in a magnetized bubble, and outside the bubble there's a spiral arm that has its own field.
Yeah.
So we wanted to see, are we seeing this guy, are we seeing this guy, or are we seeing something that is beyond? So something that is beyond towards high galactic latitude is hard because we run out of galaxy. But the poles, most likely the poles of this bubble are the same poles of the arm, because the arm is the environment, is the magnetized environment in which the bubble expands. So distinguishing the poles is hard, but we want to see, are we seeing this guy or are we seeing this guy? So the answer is towards the pole, we are not seeing the bubble, we're seeing this guy. And then in the rest is a mix. So this is what we're showing here. So this is just angle difference. So blue means very different large scale and magnetic field in the caps. So yeah, it's very different. There'll be blue, and I think this was the version of the paper I have to read, and I haven't read more. Yeah, never mind. I
Can
haven't
you
read.
also show the big linky Radcliffe Wave thing while you have the screen? The Joao will be very excited.
Well, I made this one for, well, I made this one for Gina, but I'm going to say that I made it for you.
Oh,
She's still talking to somebody.
Oh, I have to share my screen. Just a second. So this is from what Dina showed yesterday. So I assume the blue is the Radcliffe wave. Then I look at how black looks like that towards that area. This is great. Should I show this? Yeah. So this is variations in the polarization angle. So what I want you to look at is this guy. Yeah. So these are variations in the Stokes parameters. So that means bright means the Stokes parameters are changing a lot, both because of changes in polarization fraction and the orientation of the field. And black means there's little change of polarization. So this is telling that this structure there has a very well organized magnetic field.
wow. Is this corresponding to some real structure?
It's big linky, Joao.
Well, Big Link is the entire
But that's
figure.
no on the sky. That's where it is. So
No,
Yeah.
I'm talking the black filament.
the dark filament. Yeah, Catherine, you came just in time for your
Oh yeah, there is.
Another
Oh,
student.
big linky.
Oh my
that's
god,
very
I
impressive.
love Big Winky
I
though.
know you do.
I'm going to put an arrow towards what I want.
yeah, that's very impressive. Okay.
Oh.
Here.
Yeah.
I think you don't want the hour to be black.
Yeah. Yeah.
You don't see it in the blank maps.
Very, very
Sure,
impressive.
it's like, show my-
Does that make you feel better from your non-COVID symptoms?
Yeah, a little bit better. Yeah.
Attic, face. I can feel better from that. I guess just, yeah, whatever.
Yeah, if you wanna see an polarization angle, it's this. So you're dominated by the background, but there's like a little bit that is going up. If you wanna look at polarization percentage, is there. But it's in this change of Stokes parameters that you really see that there's contrast between the background and that object. So I don't know what it is. I'm tempted to call it a bone, a magnetized bone of the Radcliffe wave.
Call it whatever you want, and let's see what Thomas Henning says if you call it that. Have a nice
That's very impressive. Why would you see that one? And any idea? Is there like conditions for you to see this? They are special in some way.
Background conspiracy, like
Yeah.
if the thing is parallel to the mean field, you wouldn't see anything.
Yeah.
If it's magnetized and it's against a background that it doesn't have the same orientation, you would see it also. So I think that's why we're seeing it, because it's a little bit
different.
inclined. Yeah.
Right? Yeah.
Excellent. I'm very impressed.
You don't look sick, Joao, now that we see your face.
I'd also like
I
to
am very sick.
So on this question of, can we see actually the local bubble magnetic field when we look at Planck or not? I did a calculation that I showed last Friday, so I want to share that. Which is, the idea was just to see where on the sky are we dominated in extinction by one screen, which is the local bubble, right? And just use the Leica map. Did a very quick, drag these are the profiles of, this is one example of the differential extinction from Leica as a function of distance towards one of these pixels related to the sky. And I found where the nearby peak is, presumably that's the local bubble, and where the next, where the highest peak is in that kind of profile. So what you're seeing here is a map of where the nearest peak is, which looks a little bit different from the Fulcrum's map, by the way. Show here.
Oh, this is for Bob then. Bob wants to see this. Yeah, okay.
So, oh, you can't see. I have to share my entire desktop. sorry, 1 second.
Good thing we're recording this. We'll give Bob his 2 minutes.
So here is my quick calculation of where the nearest screen is. The color scale is the same as Pelgrim's here. And you can see that, okay, Pelgrim's has very different geometries. Okay, this blue thing I can recover over here, but the Leica map has.
So wait, I'm a little bit confused. The distance to the nearest peak thing is just, I thought when you say Leica et al. Dust profiles, are you using those dust profiles also in the lower panel?
Yeah, so for each of those pixels in the lower panel,
Yeah.
I queried the Leica dust map to
Yeah.
tell me where is the nearest peak in the dust.
The nearest peak, so it could be smaller than the.
Sure. So I queried I found the profile and I get the nearest peak and the highest peak. And I want to compare
Right.
where is the highest peak at the same distance.
I see, so basically Leica's is the highest peak and that's the nearest peak.
So Pelgrim's is the nearest.
Sorry, I meant Pelgrim, sorry.
And me here is the nearest peak. These maps should agree. They don't. So that we have to do a better calculation, I think, just to see.
Oh, now I see what you're
So
saying.
the Leica surface of the local bubble, the way I calculated it is different from the Pelgrim surface.
Oh, this is the difference with Pelgrim.
Well, no, this is just, well, by eye, you can see what the surface of the bubble would be, what the distance to the bubble is from the Leica map, and what the distance to the bubble is from the Salon map.
It kind of looks the same if it's not for that very dark red patch.
Yeah, sure. Yes, so this is very quick, but what I wanted to come to is, can we compare what the distance to the highest peak is compared to the nearest peak? So this difference map. Black says that the highest peak in column is the same as the nearest peak. The distance is 0. So the black pixels are where the local bubble is dominating the extinction. The colorful pixels are where the local bubble is not dominating the extinction.
Got it.
So in the colorful pixels, I would expect the polarization of Planck to not be dominated by the local bubble. And the black pixels, it might be, it might not be.
This makes sense. The caps are not dominated by both.
Right, I mean, the red part is the plane, the colored part on the right is basically mostly the plane. Not completely, but,
Mostly the plane. Well,
and then whatever that is. What is that?
so I think Taurus is somewhere here. I don't know what.
Orion?
Okay.
No, Ryan is on the other side. There is a region that we gave a name to in the Planck papers, and nobody ever uses. That's called Pisces.
What'd you call it?
Yeah, Pisces.
Oh, I see. Okay. Yeah, but anyway, I think this kind of, quick check was just to see where.
This is, I mean, if I understand what you're saying, is it mostly an objection to the Pelgrim's model of the bubble at some level?
No, it's mostly an objection to, well, it's sort of a test of whether your assumption, where is it bound to break down?
Right, I get that, but doesn't it also mean that you don't agree with the Pelgrim's surface?
It does.
Okay.
Yeah, but Pelgrim's already said that that's the case in the Leica 2019 versus the Longmont.
You're slow.
Yes.
I see. So what we really want is for Pelgrims to apply exactly the same technique to Leica instead of Longmont.
He did for the 2019 Leica, yeah, and he found differences.
Have to get all this data.
So Penguins doesn't agree at 2 different stages of time. No?
In the same Pelgrim's map, he applied the same methodology for the Longmont map and for the Leica 2019 map. There are differences there, but there are also some.
But the problem is it's a Leica 2019 map as opposed to the Leica 2020 map. Thank you.
And this is not the same calculation
anymore. Okay.
So Gina,
Yeah.
are you saying that the local bubble is much more pinched than the Pelgrim's model? Because you have stuff like very close by, right? If I understood the plot.
Yes, I think some of that is artifacts, I don't believe, from the Leica map at very nearby distances. But again, this was not to compute a new surface. This was just to see by eye, where would I expect the local bubble to dominate the Planck signal and polarization.
So the places where you say, can you put, oh, you stopped sharing.
I will share it.
Okay.
Yeah.
Okay. So the distance to the nearest peak. If the nearest peak were very small, okay, then I don't think it would dominate the polarization.
No, but the nearest peak is not plotted.
On the lower left, the color, the rainbow map says distance to nearest peak. Yes.
Yeah, it starts at 80.
Map for distance to the highest peak.
Right, so this is what you're asking about, Chua. You're saying that there's some stuff very close by, and
Yeah.
would that be a pinched version of the bubble? So one question there is like all this very local stuff that we've been looking at in a totally different project that has to do with the interaction of the heliosphere with the local bubble and then other things as it gets to where the sun is now. There's all this like local Leo cloud stuff Josh cares about that's like really close by. Maybe other people know about it too, but I don't know squat. But it's like tens of parsecs away from us. So could any of that stuff be the actual local clouds that are inside the bubble? And that's why they're
Maybe
gonna
that large fraction on the sky, but yeah, that's something to check.
be.
I don't think, not at least the famous ones. This is very along the plane.
It's true. Yeah, I don't know. But it would be interesting to paint that, Gina, the I believe it, I don't believe it map onto what Theo has done.
Yeah, sure.
We could do that if you want to give it to us.
Absolutely.
Yeah.
I've been staring at this too.
What's that?
This is the first moment of the distance of the Leica map.
Uh-huh.
And you could do exactly the same. You could take this, compare it to the nearest clump, and do exactly the same thing, right? Rather
It's an
than
interesting idea, sure.
right this. This I can send you the map.
Can I hold that? Can you hold it up to the-
Sorry,
Oh,
yeah.
to that camera. You have to go there. There.
Oh, hello. My laptop is dying, so I'm like holding my phone. But I can send you guys the actual.
You wanna send?
You can't see this. I'll send it to you on Slack.
Thank you.
Sorry.
See you guys?
It's so obvious. Comment, describe it, please.
Yeah, but you can see also, I mean, you can't, but there
I mean, it's beautiful.
there are also very evident artifacts of the boundaries of the Leica map. Okay, I sent it to Bob already. Let me just post it in the.
Yeah. Theo, did you get the other thing working?
No, I just made this like the other day.
You go ahead and share your screen if you like.
It's really simple. It's literally the first moment of the. So I just like took the Leica map and made it.
All right, so now we get to see what's at the top one for you.
Ah,
It's the density weight.
Yes.
Uh-huh.
Right. So on the left is the Planck derived field. On the right is that uniform one. And then I'm also working on converting FM simulations into the same form for a side-by-side comparison, but I'm not there yet.
great, thank you.
Theo, I don't really understand if the Planck, in 2D projection is showing you a uniform field in the top and bottom of the local bubble. Why doesn't your projection show that?
I have it oriented to be uniform. I'd have to pull up the actual picture of what I did. Not sure, I think is the short answer.
Okay. I would just like it to just continue in a uniform fashion. There's not that much curvature there.
But I'm sorry, Juliet, can you?
Sorry, I can show by hand in this part. If that's the top of the bubble, I would just expect the field to be doing that.
Yeah, I don't know.
Based on the Planck maps, I don't know why it does.
I don't know either.
So Theo, what is causing that circle?
The little swirl.
Right here.
Yeah.
That
I'll have to look more at that. I haven't been putting too much stock into the pulls just because the geometry here is so uncertain. So I'm not sure if
So
that
it
should be
could be
believed at
some
all. But
problem with determining the tangent plane because there's not enough stuff.
yeah, I
If
can
that's
check
true, we
that as
should
well.
just block that part out and not show it. Where there's too much uncertainty, just leave it gray.
could it be related to the problem that we're having presenting the polarization angles towards the pole? Or this is different?
It could be. I can check.
Because at some point we had problems with the pole. I would bring too much into that. I think it's center.
So here, I can share my screen for a second on Susan's behalf. Hang on.
Thank you.
You're welcome. Here's. Okay, there we go. Can you guys see that now? The people who are not sitting next to Susan on a couch?
Yes. What was the point again? Sorry, I couldn't hear because.
Oh, okay. So this is the first moment of the distance of the Leica map. In other words, this is the density weighted distance of the whole sky from the Leica map, from 50 to 500 parsecs, which I felt would be a little less artifacty. Although I can also show you the second moment, which really highlights a lot of the artifacts. Right. The point is that this would also be a pertinent comparison point to the nearest surface for the test that Gina was just doing. In other words, instead of asking the difference between the highest peak and the nearest peak, ask where the distance first moment is versus the local bubble surface.
Better metric.
Yeah.
Yeah, and what would be really interesting is to see this for all the different models.
Can you point to the
19 with the
artifacts?
20 pilgrims, I just lost track, but you know, all the different ones. Sorry, what did you say, Joelle?
Can Susan point to the artifacts?
Yeah, here, it's even clearer in the second moment, so I'm sending you that
Okay, wait,
also.
just a moment. We'll.
Thank you for letting me do this via my phone.
Here we
Sorry.
go. Is this it?
Yeah.
Oh, thank you.
Yeah, okay, so what you can
you the
particularly see,
annotation
right, is the
thing. Hang on,
artifact from the top of the box, but you can also see the octants. going
Okay,
on
wait,
below
hang
it.
on. We're gonna let Susan draw.
So which channel is this?
Ooh.
I think she said it.
Okay,
Maybe
just-
Salon.
Okay, I put it in Salon. I figure that's where we are currently.
Yeah.
Okay, hello. Okay, this is these sort of ridges are
Oh yeah.
from the top of the box now. And then, okay, how do I do my beautiful art? Okay, and then you can also see here
Yeah.
effects of
Yeah.
the octants now. It pops out more here because this is the second moment.
Yeah. Yeah,
But
thanks.
this is not to see in the first.
The first moment, did you see the Orion Eridano super bubble?
Oh yeah. It's very, very bright in the first moment.
And I can't get it.
Yeah, look at that.
Yeah, if anyone wants this map or a different version of this, a different distance cuts or whatever, or code to make this, I'm happy to give it to you.
So you did the ray tracing. Basically, you took the 3D like a map, put an observer in the middle, and did the ray tracing.
Yeah, I just projected it onto the FieldPix grid at different distances. This is nothing fancy. I mean, I made this in literally 10 minutes.
No, it's because we're doing something very evil. We are replacing, so we can take this as an input for a simulation. So you can take the 3D like a dust map as initial conditions for a simulation, and then just let it evolve with some turbulence.
Yeah.
So I had Ephraim doing something like that, but it doesn't look like this. So maybe we're dominated by the artifacts because it's, yeah. I'll show you what we do.
Yeah, I mean, I did this obviously for each distance slice, so I have this as a cube, but this, to be clear, is not a slice. This was the first moment.
Yeah.
Yeah, which is a nicely less biased, you know,
Yeah.
you don't have to make a choice.
Yeah, exactly. So, and you can just be like, oh, hey, here's this, here's that.
So Gina, you might even be able to like make it even clearer, right? If you do this for all the different ones.
Yeah, I can just give you that map, and then you can make that. Yeah.
That would be great.
So
It's 4:27, we're supposed to have an hour, so. Anything else in the last 3 minutes? Theo, I think it's fine that you, so Theo has to, when's your draft due? I should be paying attention to this.
The 5th. There's some time. I think it's not a draft anymore. It's the final version at that point.
Okay, that's right. And so there'll be a paper that we can circulate. And but I'm always the person, people who have written papers with me know this, who always want to do like one more thing. But I swear that this is not that. This is like, here's the thing. Go rip it apart. Go do more with it. Go do something else. And whoever likes it and is part of the Interstellar Institute is mine.
This is really great. Theo, where are you applying to graduate?
Ah. They're trying to recruit you to Stanford now, Theo. Be careful.
I'm not sure yet, but I will be applying this fall.
Excellent. Well, let me just
Take
remind
your mask
you.
off for a minute, Susan. Introduce yourself properly.
Remember this face now. I'm Susan Clark. I'm an assistant professor at Stanford. And my group, the Cosmic Magnetism and Interstellar Physics group, is always looking for excellent new graduate students.
And the
So
weather is great.
check us out. And you haven't been to Harvard in the winter yet, presumably. Terrible. Stanford in the winter, amazing, sunshiny, wonderful people.
It's very good for focusing.
We managed to
The
focus.
former Harvard graduate student originally from Chile just told you that Cambridge is very good for focusing in the winter.
And isn't that the bleakest thing that you could say about a
No, this campus.
Okay, okay.
Okay, we're done now. Okay, Theo, thank you so
Nice
much.
Thank you so much.
Thanks, guys.
Bye.
Bye. All right, enough of that.